state of the art in terms of speed as well as accuracy. Then we'll do a little intro to OpenDeep using the simple Net model and show some more advanced usage in the VGG and RPN portions for this model. And these acronyms, I mean, you'll understand them as we go on. So object classification, its premise is widely studied. It's given an image. What is in this image? Can you classify it for handwritten digits? Is this a 2? For an object, is this a burger? Is this a lemon? Things like that. And the two most commonly used data sets in academia are MNIST, which is actually a little bit small nowadays, and ImageNet, which is the larger competition. And the way that state-of-the-art works for object classification right now is using convolutional nets. And their main workhorse is a layer that does a convolution operation. And so a convolution is a way to take a kernel, which is this filter, as you can see here, a kernel sliding window over your input image, if you think of this as pixels. And if you just convolve the two together, you get an output for that pixel. And what this does is, in a sliding window fashion over your input image, it gives you some output feature representation that's local and takes into account surrounding context. So you're getting localized features over your input image in a sliding window fashion. And traditionally in object recognition and sort of image processing, convolutions can be done with fixed kernels to do things like edge detectors or various transformations to your input image. And for convolutional nets, what's interesting is that these kernels are actually what's being learned. So a convolutional net, in essence, it takes your input image and it learns different texture and feature extractors over that image, because convolutions essentially take out texture. Now, that's just the convolution operation for one of the layers. To do an actual classification for a full convolutional net, you guys have probably seen this type of architecture before. You basically take your input image, you have convolutional operation layer, and then you'll do something called max pooling, which just reduces the dimensionality given windows of, say, 3 by 3. It'll take the maximum value and then output that. So you're just reducing the size, the dimensionality. Then you do another convolutional layer, then you do another max pooling layer, and then finally, you'll take all those last convolution features that have been learned, condense them through your standard feed-forward network for classification. And as we've seen before, that's your dense or affine transformation layers, followed by softmax classification. And the softmax function basically generalizes logistic regression so that you're getting probabilities for each output class. So you have a large vector that's one number for every object that you're trying to classify, and each number is the probability. Is this a dog? Is this a cat? Is this a boat? What's the confidence? And what's interesting about the convolutional nets is that the filters that it learns are hierarchical because they're composed on top of each other and they're nonlinear. So they learn representations that build from lower features. So your lower level filters will learn something like lines, edges, curves, things like this. Your middle layer filters will learn more complex interactions between these textures, like circles or grid-like patterns. And then finally, on top of it, you're extracting out features that are more useful for classifying the end input image as we can see these features. Like you see honeycomb patterns, stuff like that. And convolutional nets are state-of-the-art since 2012, and they really pushed the boundaries. In the ImageNet competition, prior to 2012, people would handcraft the input features to images, like running SIFT, and they would hover around 25-ish% error. 2012 and beyond with AlexNet and more recently VGG, you get around 7.4% error in classification, which is really good given that there's so many images and classes that it's trying to detect here. So classification itself has been widely studied, and now they're just incremental increases in the ImageNet challenge every year. What's a lot harder still is to do detection. And instead of giving an image, does this have a dog, does this have a bridge in it, detection is, can you draw a box around where the bridge is and label it correctly as a bridge? Can you draw a box around every object that's in this image and correctly label what that object is? So state of the art for this detection problem is a kind of a two-stage network. One, you have region proposals. So you'll have an algorithm that will go through your image and extract out these bounding boxes. There will be many of them, normally like 2,000 of them per image. And these will be proposed regions that could have an object in it. Then you'll train a convolutional net, just like what we saw previously, on top of these regions. And all the regions would be rescaled to the same dimension so that the convolutional net can work on them. And then you'd have it classify out what could be in that image. Is this an airplane? Is it a person? Stuff like that. And traditionally, for region proposals, to calculate these bounding boxes, there are different algorithms that aren't deep nets. Stuff such as selective search is very popularly used. However, when you're trying to do this in real time, if you want an app that says, given this video input from a webcam, can you isolate out and classify, is this a person? Isolate and classify out, is this a car? These types of algorithms would be pretty slow because selective search itself adds a few seconds of latency. You're not going to get very high frame rate. So the bottleneck was using the traditional region proposals. And recently a paper came out that suggests using a convolutional net instead to find these region proposals as well. And you can get near acceptable real-time frame rates, like 5 frames a second, using this faster RCN architecture. And the reason you get the speed up is that the convolutional net you're using for the region proposals actually shares the same parameters as the convolution you're using for for classification. So you're using the same convolutional net, just a different classification layer on top of it, so the computation can be shared. So the way this region proposal network works is that first you have your convolutional neural network, the same features that you would do for classification. You get your last convolutional layer output. This is the features that you feed into this region proposal network. So it's operating on a sliding window fashion on top of the convolved features that are learned. And it'll output two sibling outputs. Basically, you have a score of whether or not this box is an object or is not an object. And the second is 4 coordinates. You're going to have the center, like x, y, and then a width and a height for a regression to get to an anchor box. So what this does for anchor boxes is that you're trying to detect multiple potential regions given an area in your convolution feature map. So you're going to get k anchor boxes. These are going to be different scales, different aspect ratios. In the paper, they use 9 of them, 3 different scales, 3 different aspect ratios, just drawing boxes around a central point in your feature map. And then the coordinate outputs are a way to kind of manipulate those boxes to kind of involve what it thinks the whole object is. So it kind of expands out or shrinks these sort of anchors along the features to fit this box around where it thinks an object would be. And then those region proposals, those boxes that it finds, as well as the score of whether it's an object or not, then get fed into the same region-based convolutional net that takes those regions, takes the convolutional features, and then outputs a classification. So what this does is it's sharing the convolutional layers so that it can be fast. And the 2 outputs are the bounding box regressions to find the size of what it thinks the object box is, as well as the probability score if it's an object or not an object. So then the RCN architecture on top is a little bit different than the one that was shown before. Because these have variable sized boxes, you can't really, you can rescale them, but that will make it harder for the algorithm to find what the object is in there. So they do something called Roi Pooling, where they take the region of interest, the ROI, the proposal that was output from the previous convolutional net, and then have a fixed size max pooling. So essentially they have a fixed number of buckets they want to max pool into, and change the size of the pooling for the layer based on the size of that layer and the size of the output, right? So it's essentially rescaling it in the max pool section. And then you're just fed through your normal fully connected layers to do your softmax output classification, as well as the bounding box fine tuning. So that's kind of the architecture that's used now for region proposal networks, and then the RCNNs. We'll do a little bit of an intro to OpenDeep, so you can kind of get an idea of the code behind it, and then I'll show you the region proposal network actually coded. So first, OpenDeep, it's kind of a lower level library than Keras is in as much as you incorporate a lot of Theano code into it yourself. So you lose some readability ease of use that way, but you get a little bit of extra, like you can do arbitrary Theano functions to your inputs to different models and kind of create graphs that way. It's kind of, in my mind, it's primarily Theano focused and secondarily gives you a nice toolbox to add standard deep learning functions on top of it. So for any core concept in deep learning, you have your input or target variables. In this case, you're going to have to use your Theano tensor types. You have your models, which could be either single layer, multi-layers, or links between them. You have your loss function, which is some cost of, how did your model perform versus what the actual value is. And then you have your optimizer function, which takes your model and your loss, can use the gradients, and does gradient descent. And you can look at OpenDeep. The docs are just out of date because it was refactored as of last Wednesday. So. Okay, I'll do a live coding demo for Linnet because it's a little small here. We'll do a simple convolutional net, Linnet 5. So for OpenDeep, the first thing, or for any deep learning model really, the first thing you look at is your data. In our case, we're going to want to define our input variable. So we're going to be using the MNIST dataset. First we can actually grab I have a wrapper for the MNIST dataset, and that gives you images of the shape 1 by 28 times 28. So you'd have your input variable, import. Your input variable is actually going to be a 4-dimensional input to the convolutional net. Your first dimension is going to be batch size. Second dimension is going to be channels for RGB. In our case, this is 1 because it's a grayscale image. And then you're going to have height and width. So actually what happens here, the MNIST data set is actually flattened, so we're going to have to reshape it back to 28 by 28. So you have your input, shape, make that. We don't know the batch size. We know that's 1 channel. We know it's 28 by 28. Now what's interesting about Theano is that you can't actually right now find a nice shape monad given an arbitrary expression. You can't just extract out what its shape is. So through OpenDeep right now, we're going to have to pass in shapes as inputs. I'm actually potentially going to work with some people with Theano to try to get this functionality in there. Actually, I should probably configure the root logger first, but so this root logger is just a debugger tool. It's going to show us various outputs so we can see what's being initialized, different arguments to our functions, stuff like that. It's just a nice thing to use. So our input shape is there, and we'll have our input be the tensor 4 of x's. And great. The output log directories already exists, so there's that. Okay, now that we have our input being this 4-dimensional input and its shape that we know from the data, we can start actually building the model that hooks into this input. So for Linnet, it consists of 2 convolutional layers and 2 fully connected layers. The convolutional layers have 20 filters 5 by 5 and then 50 filters 5 by 5. So we can make that up pretty quickly. because convolution and pooling and all these things are built into OpenDeep, just like any other framework. So the first thing we're going to want to do is, because we're making a model that's built of layers that we're defining beforehand, we're going to make a prototype which is similar to sequential or these other types of things. It basically just adds ease of use if you want to add multiple layers and have a model wrapper around it. You could also just define your own model class, but this is a little bit easier for time's sake. So we're going to want the prototype, we're going to want convolution 2Ds, and we're going to want our pooling. So there's a separate utils folder in the models because these types of layers like pooling or activation, these types of things don't actually have learnable parameters. So I like to have the separation of thought between there. So your models are going to be everything that has a learnable parameter, and your utils, which is known as a modify layer in OpenDeep code, is going to have things that don't have learnable parameters, but they still modify outputs. So we're going to get our pool. So we have our convolutions and our pools. And we're going to need dense and softmax. So our Linnet is just going to be the prototype. We're going to add our first layer to be a convolutional layer. Our inputs are going to be the input shape and input. We're going to need this tuple of shape and variable. And then we can define the things like n tab autocomplete. The n filters is 50. I think it was 5 by 5. Yeah, 50 and 5 by 5. Filter size. And then immediately you can add your pooling layer. Now, to automatically hook up inputs and outputs so that you don't have to carry over the shape and variable each time because that's annoying, you can, instead of initializing it right away with its arguments, you can specify the class and then its keyword arguments as you would, except for inputs, and it'll automatically fill in what the input should be. So pool 2D, and we're doing, I believe, 2 by 2 pooling. Yeah, 2 by 2 pooling. So that's our first convolution and pooling layer. Then we'll basically just do it again. In this case, we can safely ignore inputs because they'll be passed in. And I think our number of filters have changed. For Linnet 5, it goes 20, then 50 filters. So our first set is going to have 20 filters learned, then we're going to learn 50 filters. Great. And we're going to have the pooling. So that's our convolution layers. Now we're going to actually want to hook them up to the dense layers to do the output class probability function. And convolutions, because we're working in 3D space right now with the channels, the height, and the width, we're going to have to condense it down into the 2D space for a fully connected normal matrix multiplication network. So this is going to show a little bit of Theano code to modify the output. So we're going to have to flatten it and then show the shape. So flat input is going to be so each model, when you add it, is stored in this internal variable for prototype called models. And you can just access the last one that was made by the models to -1. Get its outputs, flatten 2. So now we just flattened the last model's output to 2 dimensions using the flatten operator from Theano. Flat shape is going to be the same thing as image shape original because our batch size isn't changing, and then we're just going to have to multiply the actual output sizes, or not the original input shape, sorry. It's the model's output shape. Nice one. So output size is also a property of the models. 0. Have to import numpy. So we're just calculating the shape from flattening. It's going to be multiplying the sizes together. Great. So going to have to be a tuple. So it's our flat input, flat shape. So now we can add our dense layer and then our classification layer. Define our inputs to be the flat shape, flat input. I believe we're going to want 500 outputs and 10H activation. So our output size is going to be 500 units, and we're going to use hyperbolic tangent. Standard stuff. And then finally, we're going to do softmax classification. So at softmax, this already configures the inputs for you. Our output size is going to be 10 for digits. And I think that's everything we need. We can specify if we want the outputs to be the actual predicted value or the probability vector. So we'll specify the outputs to be the probability vector just so we can see that. So yeah, we're going to specify out as probs to be true, and that's just an argument for the softmax layer. Now that we have our model, our convolutional model, 2 convolutional layers, 2 pooling layers, and 2 fully connected layers, we can define our cost and then our optimizer and then train it. So our loss function, well, first, let's run this type error. What I should do is just copy and paste this. Always have typos in live stuff. This is also included in the tests for OpenDeep. Prototype. Cool. So that's the same model, probably without the typo that I added somewhere in there. And okay, so we're going to grab our data set. It's going to be MNIST, which again was a wrapper that we have in OpenDeep. You can have other things like CIFAR10. You can have things that are text like Shakespeare, stuff like this. And so, as I said before, MNIST is actually, the way the data set is stored in the downloaded file is going to be 784 instead of 28 by 28 images. So we're going to have to do something to modify this data before passing it into this 4-dimensional input. So data is handled in OpenDeep as any iterable object. So you can define your own data classes. You can pass it into a streaming server, stuff like this. Anything that's iterable in Python can be used as a data set. So we can do functional compositions and kind of streaming applications on top of this to modify your data in real time as you're doing testing or training. So something we're going to have to do here is we're going to have to reshape each image from 784 into a 28 by 28 image. So we can do that easily by adding a quick function, just doing numpy reshape to the image, and then doing a simple modify stream, which is part of the data class. From the streaming training inputs, we're going to process the inputs with that function. Same thing with valid inputs, validation inputs, and test inputs. So a data object in OpenDeep has your training inputs, train targets, valid inputs, valid targets, and test inputs, test targets, and you can define all of these and then modify them as you need to. So I'm going to have to import the modify stream. So that handles our data, transforming our 784 vectors into 28 by 28 matrices. And then finally, for the model, we have our model built, and we have our data. Now we're going to want to define our loss function, and we can do some error monitoring so that we can, instead of just seeing the cost function or loss function decrease over time, we can actually see what's our classification error rate over time. Or you can define any sort of arbitrary monitor you want using Theano, like you can monitor the mean of the weights over time, or some of the gradient values, any Theano expression that you want, you can have it output during training. So for our loss input variable, our target variable we're going to compare against, it has to be, again, a Theano variable. And in our case, it's going to be digits 0 through 9. So it's going to be L vector from the tensors, from Theano.tensor, import L vector. So that's going to be our target variable y. Now our loss function, we're just going to use negative log likelihood, which is built into OpenDeep. OpenDeep.optimization.loss. And negative log likelihood is used for cost functions for any sort of probability type output, general case. So all we're going to do is make the loss between the outputs of our convolutional net and the target variable that we defined here, y. And the one hot equals false is a queue there. So one hot vectors is, instead of a digit 0 through 9, you're going to have a vector where the position is the correct class. And because we have the actual digit, it's not going to be one hot. So the probability outputs and our target for negative log likelihood for our loss. We could just train it from here, but it's nice to see what the error rate is across all images. So we can make this expression using a monitor. OpenDeep.monitor. And a monitor is just something that has a name. It's actually used for plotting. You can plot graphs of these things over time too from OpenDeep if you have Bokeh installed. So our expression, we're just going to take the mean of the model's predicted y's and our y variables where they're not equal. So this is actually Theano.mean, Theano.not equal, or Theano.tensor.mean, Theano.tensor.not equal. Our model's output y prediction, which is from softmax, and the y correct target variable. And we're going to look at it for validation and test sets as well. And now finally for our optimizer, we're just going to use standard stochastic gradient descent. You could easily use other things like RMS prop attograd. We have to define our model to be the limit that we defined here. We're going to have our loss function be our negative log likelihood, our data be MNIST, that we've modified to go back into images rather than just the 728 vector. We're going to go for, and all the hyperparameters can be defined here. 200 epochs with a batch size of 500, learning rate 0.1, these types of things. And then all we do is we train our optimizer, and we specify the monitor that we want during training. And theoretically, things work, unless I changed OpenDeep code and I get the same error. This is what happens when your code base is under rapid development. I don't know if I've actually updated this one. Look real quick under our modify layers. Okay. Yeah, this has not been updated. Oh, that's the model layer. Quick fixes. Sorry, bear with me. Or an empty list. Oops. Might have to actually wait. Oh, yes, I forgot. You have to restart the kernel when you're changing code. But I guess for the purposes, you can. I'll post this notebook up later, and you guys can run it. I don't want to waste your time doing that right now. We can go into a look at the VGGNet and the RPN, and then that's going to be it. So for VGGNet is basically the same thing as LINET, except lots more convolutions and lots more pooling. This is the VGG19 model. Disclaimer, if you try to run this on the Amazon cloud GPU, it's not going to fit in its memory. You're going to need a K40. But it basically has a lot of the same filter size convolutions in increasing number of filters as you go in processing the image. And you're going to have this for 5 convolutional layers, give or take, 2 or 3 times per of those 5. And then you're going to have 3 fully connected layers. So this is an example of, instead of using a prototype, actually creating our own model class. And so for the model class, all you need to do is you need to take an input. You define kind of your model computation. At the end, you need to define an output size, as well as these functions. So you need to define get inputs, get outputs, get params, and any other optional ones. Get switches here is for switches used for noise, so drop out during training, popular technique for regularization. We have a noise layer that adds dropout noise. You can add salt and pepper noise, Gaussian noise, things like this. So this is actually available on GitHub if you want to look at the code here, GitHub Vitruvian Science Faster RCNN. And it's a port from the Cafe version from the paper. So the second link is the paper's Cafe implementation for the model. So our VGG model is here. Our parameters. The RPN model is very simple once you have your VGG. So the VGG is the convolutional features that are shared between your region proposal net as well as your object classification net. So for the RPN, you're going to take in the convolutional net as an input, as well as some features about the image, because you need that for generating these proposal bounding boxes. What we're going to do is going to do one convolutional on top of those features that we found from the VGG. So we're going to do one convolution, 3x3 convolution. And then we're going to have 2 sibling outputs. As you saw before in the shape, you have your class scores, whether or not it's an object, and the second is going to be coordinates for the bounding box. So for our class scores, we can do another convolution, but a 1x1, which is interesting because that condenses kind of this volume into more of a classification thing. In the example here, in the image here, you're going to end up with 2 times k, which is k number of anchor boxes that you're testing out. In our case, is 9. So you're going to end up with 18 scores. The first 9 being whether or not, is this not an object? The second set of scores, is this an object? And the reason is we're using 2 scores instead of just a 1 probability object or not object is that we want to kind of have this interplay of whether or not it's not sure. It can think it's an object and not an object, stuff like that. So get your output class for as a convolution, a 1-by-1 convolution, number of classes times the number of anchors we're using. In our case, it's 9. And what we have to do to create the softmax probability is on top of this convolution 3D volume, is that we're actually going to have to flatten it down to 2D, compute the softmax on top of it, and then re-puff it up to 3D, just because Theano right now can't support softmax on top of more than 2 dimensions. So as you can see here, it's easy to incorporate Theano code into your model just by taking the outputs from your class scores, shuffling them to the number of classes, to batches, to rows, columns, flattening it to the number of classes, to batches times rows times columns, so that you can do the softmax based on the class. So you need to do your softmax based on the classes, you do some more shuffling around, and reshaping, and then finally you get the original shape again, but now it's been the softmax probabilities. And you can do your self.class probabilities to be that final softmaxed output, and you can actually specify that as being an output for your model. Similarly, the bounding box prediction regressors are going to be another convolution. This time it's going to be 4 times because you're going to want your height, width, x and y. Again, a 1-by-1 convolution. And generally in the RPN in this image, that's all you need for the outputs. It's a little bit more involved to actually get the bounding boxes from those regressor outputs. And the code is published. It's a port here. You're going to need some helper methods. So I'm not going to go through those because it's too much to go through to take those regressors from the anchors. But you can see it's just a merging of the Theano code with outputs for models. And when you wrap everything in the model class, you can easily just call a loss function on it, use an optimizer on it, things of this nature. Again, here are the links to the code if you want to check them out. Great. So in summary, this is kind of what's going on behind the scenes for state-of-the-art object detection, as well as classification. The VGG net, that one that you saw, the 19 layer that doesn't fit in GPU memory, is currently state-of-the-art. Well, an ensemble of them. The error rate is now 7.4%, which is really good considering how many classes there are. And I think Andrei Karpathy decided to take this test himself once, so he's used as like the human benchmark. And this was only, I think, 3% worse than what he was doing. But it's interesting, the algorithm makes different errors than he does. He can't get like different breeds of dogs, but the algorithm's really good at getting different breeds of dogs, whereas you can get a much broader range of objects. Object detection is a lot harder, and that's just due to you have to find these regions as well as detect within a region. So is this region an object? What is in this region? And kind of state-of-the-art is using the region proposal networks, where you get a lot of speed up by sharing convolution operations across them. So your convolutional net learns really nice features for processing your input. It'll learn nice texture extractions, and then you can use those texture extractions as the inputs to smaller networks that will then do your region proposals, pull them together, as well as your output classification given those regions. And OpenDeep is still in rapid development, but it lets you merge Theano and modular deep learning layers together, so you can create a lot of custom state-of-the-art algorithms like the RPN, which takes a lot of custom code on top of it, as well as it lets you just connect your straightforward dense softmax, convolutional layers, recurrent, autoencoder, all your base layers that you'd want. So that's it for now. And if anyone has any questions, be glad to take them. We can take them online. We can take them offline. So thanks a lot. Yeah.
This is their turn or yours?
Oh, there's.